series of webinars that CAE Associates has been providing on the capabilities of ANSYS and CivilFEM. And the first, there we go. Sorry about that. My presentation today is going to be directed towards ANSYS CivilFEM related to bridge capabilities. What ANSYS CivilFEM brings to the table is the full functionality of ANSYS in conjunction with automation and flexibility directed at civil engineering applications. And today we're going to talk about the capabilities for pre- and post-processing simulation for bridge design. Just a little background on our company. We support a very large number of customer base, both in the consulting end of our business as well as training and services, mentoring. We've been around since the early 80s. We've been an ANSYS channel partner since then, and we've been involved with civil engineering applications in a variety of different applications for the last 15, 20 years. So what is CivilFEM? So CivilFEM is a pre- and post-processor that links into ANSYS. The CivilFEM modules create a new customized ANSYS executable such that you have access to the full breadth of ANSYS capabilities, but have a series of built-in capabilities that CivilFEM has introduced. Some of these are just time-saving routines in terms of pre-processing. Some of these are actual material models for creep, for modeling rock fracture. Some of these are for post-processing, for doing load case combinations. So CivilFEM brings to the table the full breadth of ANSYS in terms of its linear, nonlinear, static, dynamic simulation capabilities, but also creates it in a means that's more user-friendly and provides access to automation capabilities that can make the construction sequence of a bridge, for example, a much easier process to perform within the ANSYS network. The developers of CivilFEM are Ingeciber. They are the ANSYS channel partner in Spain. They have a similar history in some ways to CAE Associates in that they were one of the original ANSYS channel partners. They also have ties back to John Swanson since Miguel Moreno used to work for Westinghouse. They have gone through extensive QA. Ingeciber is ISO 9001 certified. They've also gone through the nuclear QA process for Westinghouse and Areva. So they have a history of not only running all kinds of nonlinear analysis and bridge design and soil modeling, but also a very strong reputation in terms of quality assurance. Assuming everybody's familiar with ANSYS, ANSYS today is the world's largest simulation community. A very large number of users, both academically and in business. Almost all of the top 100 Fortune 100 companies have access to ANSYS. And they made a lot of strides recently in development in terms of nonlinear analysis and implementing new material laws and capabilities that are directed more towards civil engineering. And then, of course, CivilFEM is the add-on that gives us explicit capabilities in that arena. Fluid structure interaction is another area. Strength for ANSYS, recent acquisition of Fluent. Now, fluid structure interaction already existed with CFX and will be with Fluent in the next release. So what we get with ANSYS and CivilFEM is a combination of the ANSYS capabilities for for solving very large models, for very fast and efficient computational capabilities, for the full breadth of scripting and automation, in combination with the CivilFEM feature functionality. And they've been integrated together in such a way that they fully complement each other. CivilFEM distributors around the world mainly concentrated in Europe initially because that's where the origin of CivilFEM is. And, of course, you can see our office there in Connecticut. There's also distributors in South America, in South Africa, Australia. So it's truly an international list of distributors that sell and service and market the CivilFEM product. For those of you that aren't familiar with CAE Associates, we've been one of the first ANSYS channel partners. We've been an engineering consulting company since 1981. We've worked on a very large variety of problems. We do a lot of training. We do ANSYS training, we do CivilFEM training, we do any kind of combined or custom training. We've worked on, in terms of consulting areas, all kinds of different projects in the civil engineering field, nuclear steam generator replacement. We were heavily involved with NIST's investigation of the World Trade Center towers. We deal with concrete containment building, pre-stressed concrete pipes, concrete dams. And I've been interfacing with some of the people at Parsons recently on some of their bridge simulations. Technical staff at CAE Associates, everybody has advanced degrees, come from a variety of different backgrounds in terms of academic as well as industry. In terms of ANSYS Strengths, ANSYS provides us with the full breadth of capabilities in terms of nonlinear analysis, including contact, plasticity, creep, P-delta type effects, element birth and death, allowing us to model explicitly construction sequence modeling, a large library of elements from beams to pipes to shells to continuum elements. In terms of dynamic analysis, we can run, of course, modal analysis, response spectrum analysis, harmonic response, transient dynamic analysis, either using superposition or doing a nonlinear transient time marching analysis. Capabilities also include in terms of the area of thermal stress, one of the areas that ANSYS is very well known for, and the area we took advantage of for modeling some of the World Trade Center applications. Another strength of ANSYS is the core solvers. In terms of ANSYS has a sparse solver, it has iterative solvers. It can take advantage of multiple processor machines. So if you've bought one of these recent dual quad-core machines, you can run with 8 processors, for example, and speed up your runs. And all of the capabilities in ANSYS are also capabilities of CivilFEM, because CivilFEM executable, the actual executable used, is ANSYS plus the CivilFEM add-ons. So it's a linked, customized version of ANSYS. The way ANSYS and CivilFEM are integrated is ANSYS is a command-driven software. CivilFEM is also command-driven software. The difference being the CivilFEM commands start with the tilde command, or the tilde feature, to differentiate them from the ANSYS commands. There is no restriction in terms of how you integrate ANSYS and CivilFEM. So you can have a whole series of ANSYS commands integrated with your CivilFEM commands. You can use ANSYS features that may not be directly supported in terms of code checking, for example, but can still be used in the model for simulation. Capabilities in CivilFEM for code checking, for loading conditions, are all integrated over most of the more popular ANSYS elements. So you have the full breadth of between beams, shells, solids, 2D, 3D simulations. Similar to ANSYS, the CivilFEM Help capabilities consist of a full HTML-based linked help system where you can link through to the different commands available within CivilFEM, access the theory manual, which will give you detailed description of the coding of the code checking, for example, which formulas did they code. Also, in addition to a general description of capabilities, there are examples. There are simple examples where it gives you a click-by-click procedure on how to perform, and there are also advanced examples where, similar to ANSYS, where you get a log file, you get the text scripts that reproduces that particular example. You can also take those text scripts, modify them, turn them into your own customized routine. We also offer training classes to get you started. Again, we can do these either as a general training class, I believe we have one coming up in July, or we can customize the training classes and go on site. So for the next 40 minutes or so, I want to emphasize the capabilities of the bridge module. If you have a full ANSYS license, you buy the full unlimited capability of CivilFEM. It gives you not only the bridge and nonlinear analysis capabilities, it also gives you the capability to access the geotechnical module. So you can get the full breadth of CivilFEM capabilities. As an alternative, you can also purchase a reduced element version of ANSYS and get the standard CivilFEM capabilities, as well as, for instance, just linking in the bridge module. So, a quote from a bridge designer, Jorge Perez. I'll just read the first line. He says, ANSYS has always been a powerful tool in the resolution of advanced structural problems such as arch buckling, evolutionary process, construction sequence type analysis. Now, with the addition of CivilFEM, it's become a decisive instrument in the entire design and project of bridges, such as their River Sill Bridge, as shown on the right-hand side. So what are the main features of the bridge module? First, it is a series of utilities for generating common bridge sections and layouts. The layout can be done in both a combination of plan and elevation view. The geometry final model generation is automated such that once you lay out the geometry of your bridge, it's very easy to either convert that geometry into an equivalent beam model for initial design, for dynamic analysis, etc. Or you can take that same initial geometry and say, I want to build a shell model. So you can have the equivalent shell properties, tapered shells to model the bridge deck, columns, etc. Or you can have it model an explicit 3D solid model. So with the same predefined geometry, you can go ahead and create a full 3D brick model of your entire bridge segment. There are also wizards, in particular for modeling suspension bridges, arch bridges, cable stay bridges. There are a number of feature functionalities to automate the process of applying loads, in particular for the moving or vehicle loads. So you can specify you can pick, for instance, an AASHTO predefined vehicle load and prescribe that you want this to sequentially move across the bridge deck, and you can run those series of simulations, and then you can do envelope type calculations on the post-processing side to figure out what the worst case scenario is. So for instance, what's the worst case scenario if I'm designing the bending moment in the column? Which particular combinations of loads going to create the highest bending moment at that particular location? You can also simulate the construction process. It takes advantage of the full functionality of the ANSYS nonlinear birth and death capabilities. It's automated into CivilFEM, where you can specify your material properties to be time-dependent. Internally, the code will convert those to an equivalent temperature-dependent material response and model that appropriately. You can also include the effects of creep and shrinkage. And the creep and shrinkage you can either do in an equivalent modulus format, so it's a linear calculation, or you can do a time-marching solution where you can include the effects of creep, shrinkage, and aging on the concrete. In terms of the section definition capabilities, so if we're looking at the cross-section of a slab-based or box girder section, we have an option for the Briggs Section Explorer. There's a general explorer that you can make any predefined or any kind of cross-section. The Bridge Explorer just makes it a little more faster and automated to make a series of sections where they have been reduced down to a small number of parameters to define to generate those sections. You can run these interactively, or you can run these in a command level. So you can set up, if you have a whole series of them, you're just changing one number, you create an input script that runs through and automatically constructs your bridge based on the whole series of cross-sectional entities. So if we take an example, look at some of the slab operations. We, of course, can just create a straight rectangular slab. There's also some polygonal sections where you can have a variable thickness type slab. The slab definition gives you a window. You input the parameters, has a sketch on what it looks like. It also will show you the final geometry as it's being created. You can zoom in and out, print it, make modifications. And again, any of these operations will be written, the equivalent capabilities will be written to the log file for operation in terms of taking this data and turning it into a script input file for running simulation. So the slab sections, another capability within the slab section module is the ability to put holes. So you can put in a series of holes in your slab section. You can have these holes be continuous, where they may run the full length of the bridge, or they can be discontinuous, where, for instance, at the column supports, it can be, again, a solid section. And again, each of these cells allow you to define, there's a straightforward description. Also, the sections, there's an element size for meshing. The meshing will be used to determine if it's a beam model where the integration points will be defined for defining the integration of the beam section. If it is a 3D solid model, that's explicitly what the final mesh will look like when you extrude the model. So if we have a thin-walled section, we can use, instead of the solid section preprocessor, we can go and use the box section module. The box section module is going to allow us to prescribe the general parameters of our cross-section, so widths and heights and number of cells. And then once we've created those cells, we can actually make modifications to it. We can make tapers, we can make local radii in the webs, etc. So with a series of pull-down GUIs, with a very short amount of time, you can build some very complex cross-sections. You can make modifications to those cross-sections, put a crown on for the water being traveled to the sides. You can also edit the various features in terms of the number of divisions, for instance, in terms of the meshing on the top and bottom of the flange. The only requirement is that the section has to be a continuous box. It has to go from one end to the other as a continuous section. Now, you could break your bridge up into multiple sections if you wanted to, but if you're going to extrude along a pathway, of course, the cross-section has to be continuous. And this slide just shows what the equivalent commands would be to perform certain operations. So this is using some of the APDL scripting of CivilFEM. So you may do interactively, maybe you build one cross-section and then you build a whole series of them by cutting and pasting and editing these files. You can also do mathematical operations. Any of these items can be also replaced with parameters, where those parameters could be driven by, for instance, a design optimization capability within ANSYS. There's a lot of flexibility in terms of automation, but also just general application for any custom design or custom sections with the bridge design modeler. So once you define your sections or series of sections, the next step would be to lay out in plan and elevation view the actual bridge span. So we can perform with the bridge layout capabilities a definition of straight curved sections. We specify what CivilFEM terms mileage points, and each of these mileage points we can have a starting and ending radius, if applicable, coming into these. And we can also force it to do a spline fit between various radii as well. So you can have it create a curved representation combining the various different straight or curved sections that we create, so we get a continuous length of the layout of our bridge. Once we've laid out the plan view, now we can go to the elevation view and modify the elevation of the various mileage points along the length of the span of the bridge. And each of these spans, if they, for instance, two different spans form a sharp angle, CivilFEM will automatically put a parabolic approximation in there. And then, of course, this is highly distorted, but just showing as an illustration of putting a parabolic fillet to connect the two straight sections with different angles. And it's just showing that once you define some of your entities, you can go ahead and plot the sketches. You can also, then what you can do is assign the cross-sections predefined at the particular locations along the length of the span. It'll automatically extrude between cross-sections to get you a continuous mesh. And again, this mesh can either be beams, shells, or 3D solids. You can also put in a offset relative to the center line of the definition of the layout of the bridge. And in addition, we can put banks in, we can put skewed section, and in regions we can make the beam or the model solid or hollow. So just a couple plots just showing the definition of some sections and then extruding those along the length. And again, this extrusion can be either to make beam elements, shell elements, or 3D solids. So here's just an example of the concrete slab, just a couple slabs with the appropriate model generation being performed. All of the capabilities are driven either through the GUI, so you can see on the left-hand side, up above, this is the CivilFEM capabilities are an add-on to the traditional ANSYS menu. So on the left-hand side, we have the traditional ANSYS layout GUI, and then we have the Civil definition for all of the CivilFEM capabilities. Other capabilities for quickly defining different bridge types. There are a series of bridge wizards. The wizards include capabilities for cable-stayed bridges, arched bridges, suspension bridges, where the geometry is predefined with a small number of input parameters, maybe 5, 10, 15 input parameters will define a complete bridge. A couple examples just shows the GUI layout of a couple different suspension operations. They can be steel, they can be concrete. You can use the existing concrete slabs that you create, or you can use a mixture. So very general capabilities, but also very quick automation to generate a bridge definition with a very small number of inputs. So just a little more definition here is an example showing a concrete suspension bridge, and also the cross-section that was defined can be imported to define as the deck section for this particular bridge. A couple more examples just of a steel frame type bridge, a concrete deck bridge section, and there's no limitations really based on you can make a series and combination bridge. You could use some of these predefined entities along with using any of the standard ANSYS capabilities or any other features, so you could tie these different types of bridges together as well. Moving on to loads. So for loading environment to load our bridge, the loading capabilities use ANSYS direct commands in terms of putting on pressures, accelerations, forces, moments, but a lot of these have been automated. So the CivilFEM capabilities will automatically generate the, for instance, surface effect elements to prescribe a mobile load on your bridge deck. It'll take those and prescribe the appropriate scaling factors for those loads based on code definitions. And so it can allow you very fast and efficiently to define a very large number of different loading conditions. These loading conditions are analyzed individually but can be grouped into different families, and the reason for grouping into families is for the load combination capabilities within CivilFEM. So, for example, if I want to run a case where I want to take one of the worst case scenarios of that group of loads, then I'll select from the family of the various independent loads and tell CivilFEM, select me the worst case scenario from that group. There is a wizard or combination explorer that allows you to drag and drop the various different combinations, load combinations that you want to analyze. So you can either do it in a scripted batch type mode, or you can do an interactive drag and drop type mode to specify your different loads. For each family, for each load factor coefficients, you can specify the coefficients explicitly, so it's a dead load, maybe it's 1.0, or you can make them variable coefficients, where you can say this coefficient can range between 0.9 and 1.5, and give me the worst case scenario. The vehicle loads allow us to simulate both a rigid type vehicle, truck, or a flexible type vehicle, such as a train. Each of those definitions automatically are set up around the axis of the road that we've defined. So the user input is very limited to calculate some very complex loading conditions. So one of the things the input is that you prescribe when the first vehicle ends and the last vehicle leaves, how many vehicles you have on the bridge at any one point in time. It'll come up with the various different loading scenarios. So the loading scenarios from the vehicle, very powerful. You can also combine that with any user-defined loads, such as snow loads, other dead loads, or live loads, etc. Another strength of CivilFEM is in the area of pre- and post-tensioning. There is an automated capability for prescribing the loading conditions from pre-tension or post-tension tendons. One of the things the CivilFEM allows you to do is prescribe the path of the tendon, and it doesn't have to line up explicitly with the nodes and elements of the continuum with your model. So I can prescribe the tendon geometry with a single line or a series of lines for a series of tendons. And then if I was modeling, for instance, a 3D solid, CivilFEM will figure out where those tendons would enter and exit the individual elements and come up with the equivalent force balance to create those loads on the structure. It allows you to create a finite element mesh that prescribes or describes the geometry without having to have a very complex definition to try to incorporate all of the tendon paths. Again, there is a wizard or tendon editor that allows you to prescribe the definition of the tendons both in an elevation and plan view, and you can then take those tendon loads and transfer them over to the solid, either the beam, shell, or 3D brick finite element model. In terms of post-processing, at each section in the model, whether it be a beam section or a solid section or shell section, we can extract forces and moments, stresses and strains, utilization factors based on code checking. A couple examples shown here. Some of the post-processing windows showing you a stress distribution in a couple of different cross-sections. Load case combinations allow us to prescribe the worst case scenario combination of loads, so on a particular location or entity within our, in this case, our bridge. So for instance, we're looking for the maximum axial stress at point P. We can figure out, or let CivilFEM figure out, given the potential location of the locomotive, which would produce the worst case scenario moment at that particular location. Combinations are general. They can be combinations with mobile loads, combinations with variable coefficients. They can be combinations with different directions for wind and seismic, combinations according to particular code specifications. And so we can have a variable coefficients where we have a constant coefficient for the dead weight, we have variable coefficients for traffic, we can have uniformly distributed or non-uniformly distributed loads. There are capabilities for specifying per code capabilities. CivilFEM supports a wide variety of codes, a number of different European codes, Chinese codes, Russian codes, and the U.S., ACI, AASHTO, Caltrans, AISC are some of the codes supported. ACI 349, 359, a number of different codes have been implemented into CivilFEM. Load case combinations, again, we can have a very large number of combinations. You can have up to 1 million different combinations. Combinations rules can be nested, so we're looking at various adding the effects of gravity, dead load, live load, wind load, vehicle load, and coming up with a worst case scenario for different locations in terms of the design process for our bridge. And this just highlights the Combination Explorer again, where in the lower right-hand corner we have all the different loading environments that have been generated as individual or as combinations, and then in the upper left-hand corner the actual physical combinations, what they're made of. So combination 1 is a snow load, it's got self-weight, snow load, and wind as part of that particular combination. And as part of these combinations, again, we can have variable coefficients. So, for instance, a scaling factor on the loading for the snow load could be, in this case, showing a range 1.35 to 1.0, or maybe it's from 0 to 1.35, etc. Code checking capabilities in CivilFEM and CivilFEM Bridge module in terms of post-processing. We can isolate forces and moments on individual components of our model. From concrete sections, it will do the force moment, axial force, bending moment interaction diagram. It'll create the interaction diagram and show you where you are within the interaction diagram, and then scale your result relative to that location. So the bottom left-hand corner, we're actually got a utilization of 3.4. We're outside of the envelope, so that design does not work. If we are inside, maybe we have a utilization of 0.9, 0.8, 0.7. It automatically figures out the distance to the closest point on the envelope from where we are with our given force and moment. In terms of nonlinear analysis capability, since CivilFEM accesses the full ANSYS capability, we can have material nonlinearities, geometric nonlinearities, contact nonlinearities. In the area of concrete, CivilFEM has some special features for taking into account creep and shrinkage and time-dependent strengthening of material. The total strain calculated will be a combination of the elastic strain, the creep strain, and the shrinkage strain. Strain due to shrinkage is at 0 time. Strain during creep is time-dependent. The creep definition is assumed to be proportional to the stress, so we have a creep law built in that's stress proportional. We can look at the effects of creep in terms of superposition, assuming that the creep strains can be superimposed with other loads. We can also run a physical time marching response where we're actually modeling explicitly the accumulation of creep, where it's not we're not dealing with superposition. We can define our material properties that can be temperature, time dependent. We can compute the shrinkage capabilities uses a thermal analogy, but the creep analysis actually does a field time marching solution. For creep and shrinkage, we can specify activation times for our material. This is also in conjunction with the construction sequence simulation. And CivilFEM supports a wide variety of ANSYS element types and feature functionality. So step-by-step integral, we solve the full creep equations in ANSYS. CivilFEM has user-defined creep laws that have been incorporated. So we can compute creep strains incrementally based on the parameters, coefficients defined within the creep law in CivilFEM. We can also include the effect of aging, so we can add an additional coefficient to our creep strain increment, and this can either be done by using the built-in algorithm in CivilFEM, or you can actually adjust that parameter as well. If our loading remains relatively constant, then it may be save us a lot of computational effort by just modeling the creep as an effective modulus. So there is also the capability of coming up with an effective modulus where we can model the effect of the stiffness of the concrete plus the creep effect by just adjusting our modulus and getting then the elastic strain will be really a combination of the mechanical strain and the creep strain. In terms of availability of different element types, if we're doing the time marching step-by-step method, then since CivilFEM is leveraging the creep capabilities in ANSYS, it's using the explicit or the implicit creep capabilities that are hooked into the 180 series elements of ANSYS. If we're using the effective modulus method, it doesn't matter. It's really applicable to all the ANSYS element types. And this is just an input script just demonstrating where we would specify a series of times, if we're using units of days, and simply specify an activation time at the different times that we're solving for so that CivilFEM correctly interprets our material law and grabs the appropriate representation of the material properties at that particular time. Another capability within CivilFEM is for construction sequence. The construction sequence can be relative to the entire structure in terms of activating various spans, or it can also be the process of activating relative different materials within an individual beam element, for example. So if we're going to model this bridge right here with beam elements and the actual construction processes to construct the steel bridge without any underlying supports and then pour the concrete on top, the stress state is quite different with that condition than it would be if it was fully supported, such that basically the steel and concrete both came alive in a stress-free condition. So with the incremental procedure, we can specify a different activation time than the concrete and the steel. We can also include the effects of the dead load of the concrete when it gets porous, but no actual stiffness effects will be included in the simulation. When it comes to a cable-supported bridge, an incremental construction process, we can build the entire bridge first, but then using the activation time, you can get the net effect of only the portion of the bridge that actually is truly active at that point in time. And the subsequent portions or subsequent entities will come on in a stress-free condition. So they come in a deformed shape, but in a stress and strain-free condition. That's just one of the commands showing the activation of construction step where CivilFEM gives you a little more capabilities in operations than just the standard ANSYS birth and death features. And this is just an example from the construction process sequence of constructing this three-span operation where phase one, first span, second span, third span. And if we look at the moment diagrams in terms of the operation, we see the variation in the moment from the phase one, phase two, and phase three. Finally, as a case study, this is the Slow River Bridge. It's a combination of a arch bridge in the middle and a segmental box-type structure or steel frame on the ends. The unique feature of this bridge is the fact that we want to capture correctly the combination of the two different bridge types and make sure at that intersection that we appropriately model and capture the forces and moments that are created by the incremental construction process. So a beam model approach was used. In the upper left-hand corner there is the beam model. The columns were ignored in this particular model, just used as supports. The geometry of the various sections, there are some link sections. They're modeled with hollow pipes. The box sections are modeled with the box, and some of those are composite sections, a combination of steel and concrete, or a concrete deck and a steel underlying framework. A construction sequence simulation was used to develop the fact that the concrete would be poured stress-free after the steel box had already been developed. In the lower left-hand corner, we're just seeing the equivalent beam model showing the section property or the section geometry of some of the beam elements. Then the axial force and bending moment diagrams were also provided just to demonstrate some of the post-processing features of the bridge module of CivilFEM. The figure in the upper left-hand corner is just a GUI shot of taking the cross-section, showing the stresses and forces and moments in a section of the composite bridge section. For the concrete slab, it's modeled with, in this case, in the right-hand corner with shell element section and showing the equivalent amount of reinforcing required on the bottom surface. In the reinforcing design capabilities of CivilFEM, you need to specify a cover and an initial cross-sectional area of rebar, but you can have the code go ahead and do a design process where it will figure out how much additional rebar is needed, for instance, if the initial guess under-designs the section. And the left corner shows a sub-modeling approach for the tie between the arch section and the box section of the bridge. And so displacement response from the global model was imposed in the local model, where now we could develop the detailed stress results. Those are von Mises stresses in the actual connection, which is modeled explicitly with shells. And then finally, in the lower right-hand corner, again, is the interaction diagram and utilization. This is showing that the design is safe for this because the green dot is inside the envelope of the interaction diagram of axial and bending moment. So that is a overview of the nonlinear bridge module in ANSYS. The other webinars previously given include the just general CivilFEM overview, talks a little bit more about the various box section capabilities, the ability to model various different members, a little more on the code checking, and general features of CivilFEM. There's also was a webinar on geotechnical applications, and both of those are accessible via the web where you can download those presentations. Upcoming, we're going to be attending the Bridge Conference in a couple weeks in Pittsburgh, and then the final of the series of webinars in terms of CivilFEM capabilities is the nuclear applications, which will be in the first week of July. I don't see any questions in the chat, but I'll have Christina go ahead and unmute the phones, and if there's any particular questions I can answer for anybody, please do so. It doesn't look like she's actually unmuted. I still see the little X box.